Hello, everybody. This is going to be all about momentum. So momentum is represented with, let me get a black pen, the variable p. It is a vector quantity, which means the direction matters, and it has units of kilogram meter per second. And so what momentum is, and it's actually kind of similar to how we would say, or how we would use momentum in everyday life. So if we talk about like momentum in everyday life, it's usually in a sports context, like, oh, that soccer team has a lot of momentum, like their momentum's really going, they got it up, they're like, hard to stop, they're unstoppable. And that's kind of what the meaning of momentum in physics is. So momentum is how hard it is to stop a moving object. Okay. And if we think about trying to stop moving objects, it's going to be really difficult to stop fast objects. And it's also going to be really hard to stop large objects, right? Like the bigger the object, the harder it is to stop, and maybe the faster it is, the harder it is to stop. So that tells me that likely momentum is going to be based off of the velocity and also the mass of the object. Okay. So the equation for momentum actually ends up being kind of exactly that. It's momentum equals mass times velocity. And that's where we get the units from, because mass is measured in kilograms and velocity is measured in meters per second. So when we put that together, we get kilogram meters per second. And unfortunately, there's no like Newton or Joule or, some sort of what's called a derived unit for momentum. We're just stuck saying kilogram meter per second. Now, you might be wondering, like, momentum kind of reminds me of inertia. So how is it different? So the answer is this, is inertia is an object's, is an object's resistance to any change in velocity. So that could be starting, stopping, etc. Right? Any change in velocity, and it's only based on mass, right? So momentum is how hard it is to stop a moving object, and it's based off of how fast and how large. Inertia is an object's resistance to any change in velocity. It's the idea that an object is going to keep doing what it's doing unless an external force acts on it. And that is only based on the mass of an object. So they are two different things. We also don't really calculate or measure inertia. Inertia is a relative measurement. And when I say measurement, that's kind of like in quotes, right? So like a bus, we can't say that a bus has big or small inertia because we need to compare it to something. But like a bus would have greater inertia than a person. Okay? But with momentum, a bus and a person could have the same momentum if the person was moving very fast. Okay, so that's the difference between momentum and inertia. Just keep that in mind as we move forward. Also keep in mind that because momentum is a vector, momentum can be negative. Negative, that just means negative direction, right? So our negative directions are usually left and down. So if an object is moving left or down, then we would say its momentum is negative. Okay? So that's how we calculate momentum. There are a couple of cool ways that we can show momentum or kind of, give a visual of momentum. And of course, the first is going to be vectors on a grid. right? And we are used to this with forces and free body diagrams, and we kind of are able to show that, you know, if two arrows cover the same amount of boxes, then those two forces are equal. We kind of do the same thing with momentum. So let's say that we had a momentum vector, aka a momentum arrow. That was 1, 2, 3, 4. That's terribly spaced, but pretend it is. So this is like 4 boxes, so to speak, right? That would have the same momentum as 3, 4. This is also 4 boxes. So we could say that the magnitudes of the momentum are equal. Magnitudes are equal. Remember, magnitude just means amount, but they're just in different directions. Okay. So it's not that these are, you know, different momentums. They're the same momentum, just in different direction. Okay. As with energy, we also have these kind of, I call them quote unquote bar charts, because they are bar charts, but not in like the traditional sense. So one way that College Board likes to represent momentum, especially in those workbook problems, is with velocity mass bars. And I'm not going to call them graphs, I'm going to call them charts, because we wouldn't really graph velocity versus mass, because that's not really a thing we would graph. So they really are charts and not graphs. So what we would see is we would see a bar here, and this would represent a small mass because it's not very wide, but the mass is represented by the width of the bar, and this would have a large velocity, and that would be represented by the height of the bar. And then the area of the bar would equal the width times the height, because it is a rectangle, which would really represent the mass times the velocity. So the area of this bar would equal our momentum. You might be wondering, why is momentum represented with a P? I think it harkens back to like the Latin or something. It's like, I don't really know, but I think it has something to do with Latin. So like I said, it's kind of like an interesting bar chart, not the same way that we did bar charts with energy, but still pretty useful, right? The width represents the mass, the height represents the velocity, and we could use the area to represent the momentum. So another object could have the same momentum if it has the same area. So this bar could represent an object with the same momentum, but this object would have a large mass and a small velocity, right? But the area here and the area here are approximately the same. So we could say that they have equal magnitude and momentum. And then I could also show, of course, negative velocity or negative momentum by just flipping my bar into that negative velocity axis. So this would represent a negative momentum, aka a negative velocity, which just means that I'm like moving left or down in one of those negative directions. So those are two ways that we can represent visually the momentum of an object. So that's momentum of single objects, but what if we have multiple objects in our system, right? So we have our total momentum of our system. And we know from math class that total usually means add, right? But because momentum is a vector, we have to make sure that we're doing vector addition, which means we take into account the direction. Okay. So let's say I had a system where I had two objects, both moving with a momentum P, okay, and they're both moving to the right. So that system would have a total momentum of 2P. Right? If I had a similar two object system, but this time my objects were moving in opposite directions, this would give me a momentum of 0P. Okay? Now remember, what I'm really doing here when I'm doing my total momentums is this momentum is really the mass of this object times the velocity, the mass of this object times the velocity. So here what I'm doing is like m1v1 plus m2v2, whereas down here I'm doing a negative m1v1 since it's moving to the left plus m2v2. And I'm saying that the values here of m1 times m2, or sorry, yeah, m1 times v1 and m2 times v2, they're the same values, which is why I get like 2p and 0p. So one of the last ways we might be asked to vector add is if I have two objects, one with a momentum to the right and one with a momentum upwards. So we notice that I drew them tip to tail because that's kind of how we do proper vector addition. And then the resultant, or the total momentum, goes start to finish. Okay, and I just drew out a right triangle, so that tells me my total momentum is going to equal my individual momentums in Pythagorean theorem. So my total momentum would equal, remember those p's really represent m's times v's, so m1v1 squared plus m2v2 squared. And I can't like pull out the squareds because that's not how algebra works. All right, and so the last thing we're going to talk about that comes in with total momentum is this idea of center of mass velocity. So we've talked about center of mass kind of like briefly in the sense that if we have two masses, the center of mass is sort of like the balance point of the system. If the two masses were the same, the center of mass would be exactly in the center. And then since 2m is heavier, the center of mass shifts closer to it. Okay? So when we talk about center of mass velocity, that usually means that these objects are moving, and I want to know how fast is that dotted line moving. So I want to know how fast is the center of mass going. Okay. So in a one object system, the velocity of the center of mass, which I abbreviate COM, is just going to equal to the velocity of the object, right? There's only one object in our system, so the center of mass is just that object. In a two object system, the momentum of the system is really going to be the total mass times the velocity of the center of mass, which we showed above is the momentum of the first object plus the momentum of the second, right? Of course, a vector added together. Okay, so if one's negative, just make sure to subtract it. So if I wanted to find the velocity of the center of mass, I could find the total system momentum and divide by the total mass. So let's just do a quick example so you see what I'm talking about. So let's say I have a 3 kilogram mass moving to the right at 2 meters per second. And then I have a 2 kilogram mass moving to the left at 2 meters per second. Actually, it looks like in my notes I made this a 4 kilogram mass. Okay. So if I wanted to find the velocity of the center of mass, the first thing I would do is I would find the momentum of the system. And I would do that by doing the mass of the first object times the velocity of the first, m2 v2. And since they're both kind of parallel directions, meaning not perpendicular, I'm not going to worry about any Pythagorean theorem. So m1 is 3 kilograms, v1 2 meters a second. This is 4 kilograms, and I'm making sure to plug this in as a negative 2 meters a second. So this gives me 6 plus negative 8. And so that gives me negative 2. Remember, the units are kilogram meters per second. So once I have that momentum of the system, I can set that equal to my total mass times the velocity of my center of mass. So my total mass ends up being 7 kilograms. Negative 2 kilogram meters per second. So I'm going to divide both sides by 7. So the velocity of my center of mass is negative 2/7 meters per second. So that dashed line here would move to the left at a speed of 2/7 meters per second. Okay. Now, if I have two objects, let's say they're 3 kilograms and 2 meters a second, and this one's also 3 kilograms, but 2 meters a second to the right, or to the left, here, my total momentum would be 0. So that means the velocity of the center of mass, no matter what the total mass is going to be, the velocity of the center of mass is 0. So that dotted line, which would end up being right in the center, would appear not to move if it existed in real life. Okay. So that's how we find the velocity of the center of mass. One thing that might be helpful to know is how to actually figure out where the position of that center of mass is, maybe at some starting point. So the way that we find that is actually kind of similar to how we find the velocity, because if you think about it, that velocity of the center of mass is really like m1 v1 plus m2 v2, you know, however many objects, all over the total mass. So the position of the center of mass follows the same format, just instead of v's, it's position. So m1 x1 plus m2 x2, however many objects there are, all over m total. Of course, making sure that we are paying attention to any positives versus negatives. And that's really it about momentum, which again measures how difficult it is to stop an object.